Hello, hello. Am I audible? I guess it's just two of us here, so maybe we'll wait for another 2 minutes and then we'll begin the session. Maybe at 7:10 we can begin. I hope others will also join by that time. Okay, so I think we'll start today's session. Good evening and welcome to today's tutorial on urban utilities and planning, water supply, sanitation and drainage. So today we'll be discussing about week four, the like based on the lecture, some assignment questions and problems. So sorry, week five. My bad. Week five. We'll be discussing about week five. So what we learned in week five was that we learned about different distribution system, the layout on how we distribute water. So till the previous weeks we learned about pumps, where do we locate the pumps, etc. And now we're moving on to distribution systems, so pipe design. We saw conveyance of water. How do we design the radius of the pipes, different formulas for using that, all that we discussed. Then we also, in the last two lectures, we also saw about pipes, joints, and metering, what kind of metering is done, how do we measure, and some smart systems also, SCADA-based smart systems also we discussed. And finally, in the last lecture, we saw how distribution networks are designed. A simple loop system, a complex system, or a both simple and complex together, and what are the different methods we use in order to solve this network, on how much discharge will be there through each pipe, or what will be the head loss in each pipe. So all those calculations also we saw. So this week had a bit of formulas and numericals, but that's all good for the understanding. And in assignments, we don't have any complex calculations, so it's fine. Whatever calculations are there in the assignment, we will solve similar kind of questions right now here today. So yeah, so this I guess both of you have already been there for the previous session, so you already know how we go about the session. So let's directly get into the questions. So the first question is, wait, let me just confirm. I'm audible and my screen visible. Everything is fine, right?
Yes.
Okay, thank you. Thank you for the confirmation. Since it's just both of you, I would request both of you to be a bit more interactive so that at least I know that it's reaching across and it's just us. So, yeah. So, let's go to the first question. The carrying capacity of water distribution pipes directly depends upon which of the following factors? So, yeah, since it's just both of us, let's each of us take a question and then go. So, Vaishaka, can you attempt this question?
A size of pipe.
You say a size of, so there can be multiple answers correct for this. So, size of pipe, you say size of pipe, the carrying capacity depends on size of pipe. Okay, fine. What else?
Sir, ma'am, velocity of flow.
Velocity of flow.
Okay, Partha, you saying velocity of flow, it also depends. Fine. What about pipe material? Does it depend? Any of you? Yes, no, yes, no. Actually, I can't hear. Did you say something?
Maybe, ma'am.
Maybe a little bit carrying capacity.
Little bit. Okay, so there's some ambiguity in that. Maybe. This both a yes, but this is maybe. Last one, thickness of pipe. Does it or does it not? Maybe again.
Yeah.
Maybe again. Okay, this both there's doubt. Okay, let's go option by option. Size of pipe, obviously. So that both of you have agreed. I'm just explaining it. So if you have size by size of pipe, what we're mainly talking about is a radius. So as the radius increases, the more water it can carry, right? Because now there's more there's more volume or there's more space to carry more water. So obviously the carrying capacity will increase as size increases. So that is correct. Now velocity of flow, by velocity of flow we are mainly talking about the discharge or the rate at which water is being supplied in a distribution system. So when the velocity of flow also increases, you can carry more water in a short period of time. So carrying capacity increases based on velocity of flow. So that I guess both of you don't have any doubts in that. So now what happens to pipe material? So it's a maybe which you said, but yeah, pipe material actually influences the carrying capacity. How? Because there's something called viscosity, which you might have seen in this lecture. So it's a property of any fluid. In simple terms, it's friction for a fluid. So in normal uh, roads or any surfaces, if you want to roll something over it, if it has more friction, then it'll be more difficult to roll something over that, right? Or the movement on a path becomes more difficult when there's friction. In some cases, it is useful because it's because of the friction that there's some grip on that. Like for instance, if it's a road, you try to increase if it's a road, you try to increase the friction so that there is the vehicle can be there on the road without slipping through it. So when it comes to water or flow of any fluid for that matter, whenever fluid touches any surface, like there is some amount of viscosity or there is some drag. Like fluid is viscous in nature, that's a property of a fluid, and the material contributes towards this. For instance, if there is a pipe through which water is, or any fluid, not just water, this is a general phenomenon for any fluid, if it's flowing, the velocity on the center of the pipe will be higher than the velocity in the sides of the pipe. So it usually takes a shape in this form. And this is normally called the terminal velocity, which is the main velocity, and then there's a reduction in velocity over here. So this reduction is called because of the viscous nature of the fluid. There is some amount of viscosity or drag which is caused onto this fluid. Now this changes with respect to change in the material property. For instance, if this is a very smooth surface, then the viscosity will be less, and you call the flow to be, so any fluid flowing through a pipe, it's mainly laminar flow because it's taking the shape of the pipe, it's going along the direction of the pipe. So there are two types of flows. You have the laminar flow and you have turbulent flow. So this in our lecture this time we discussed. how do we differentiate between laminar and tubular flow is by using something called as Reynolds number. So if the Reynolds number is less, then the flow is laminar. If the Reynolds number is more, then the flow is turbulent. So in pipe, if it's a very large pipe, then and if it's a flowing pipe, mainly the laminar flow is very prominent towards the edges of the pipe because it is touching the surface. So to this laminar flow, the surface of the pipe causes some amount of friction. So if it is a material with high frictional properties, or if it's a very rough surface, then this disruption. So friction by means, it means that it is causing some. So there is some resistance to movement. So this gives more resistance to movement, and because of this resistance, the velocity in these sides reduces. The terminal velocity. So this has an influence on this velocity also, because from the sides. So for because of this, at certain instances, the terminal velocity may also reduce. So now this again depends upon the diameter of the pipe. If it's a higher diameter of pipe, then the influence of the material or the resistance of the material might not be very prominent in the central area. But if it is a small pipe, then the resistance of the material is more prominent. So just to say that material of pipe influences the carrying capacity. So if it's a very rough material, then it causes more friction, or it disturbs the viscosity, or it creates more resistance to the existing direction in which the flow is there, and because of that the carrying capacity can reduce. So pipe material influences carrying capacity. Now the last one, thickness of pipe. So thickness of pipe, again, how many of you feel it influences? uh,
No,
Actually, it depends upon the place, man. Thickness, maybe.
okay, somebody said no, it doesn't influence. Can you give your reasoning why you feel it does not influence?
no, sorry. Actually, if it's affecting effective diameter or effective area, then it will influence. Because
Correct.
outer thickness will not influence.
Correct. Exactly the point. Yes. So only if it affects the inner diameter or inner radius. So if you have a pipe, if you have two pipes, this both has radius r. If you assume that they both have radius r, and the thickness of this has got like probably zero point 0.2 mm thickness, and this is around 5 mm thickness. Just by increasing the thickness of the pipe, the carrying capacity will not change because the radius is the same. But if that is influencing the radius, then it will. So by default, if you say just the thickness of the pipe, it does not influence the carrying capacity. Because by thickness, what we are mainly talking about is the outer thickness. We are not talking about the inside radius. When you're talking about the inside radius, you're talking about the size of the pipe. By the definition, size of pipe means that we are talking about the radius or diameter of the pipe. So the answer to this is that the size of pipe, velocity, and pipe material influences the carrying capacity, but thickness does not influence the carrying capacity. Right? Shall we move to the next question? Yes.
Yes.
Okay, thank you. Thank you for that confirmation. So next question is we have to match the following with the correct option. So we have gravity system, dual system, and pumping system. So let's see which of the following is a gravity system, one, two, or three.
3.
Three, yes, that's a very simple. So you have a reservoir on top, and by means of gravity, the water is brought down into the town area, and there is no other pumping or anything which is involved in this. So correct. So three is gravity system. Now dual system,
One, man.
one is dual system. Okay, so why is one dual system?
Both it has pump house and the elevated reservoir.
Pump house and elevated reservoir. Okay, okay. By what do you mean by dual system?
Like it can we can have it straightly from through pumping, or we can have it like elevator we add reservoir. So from that also we can separately have the supply.
Uh, No, that's not. So, by dual system, you're talking about, yes, you have a reservoir. So, you have two pumps. Like, you have an intake from which you intake, and then you have an underground reservoir, or you say store that. And then you have an elevated reservoir, so you again have one more system by which you are pumping it over here. So you have a dual approach. Yes, you're partially right. Like what you meant, I understood what you meant to say is right. You have two intakes coming, but just and in these two, for instance, if you yeah, here you basically you're saying that you're pumping it twice in this. You're taking
Yes,
it
ma'am.
from here, you're taking it from here also. You're pumping it twice. So that's what you call a dual system. So this one constitutes a dual system, not only because it has an elevated reservoir. If it didn't have an elevated reservoir, but if it had some other reservoir where you're storing it, then also the whole idea is you're pumping it. You're having an elevated reservoir, you're pumping it to the reservoir also, and then you have two systems in place. So you're partially right, but maybe the way you phrased it was a bit different. So yeah, so it's a dual system. And then your pumping system, yes, you have the pumping system because you're taking it, and then you just have the pump house to pump it directly into these places. That's it. So that the final one, you have the pumping system. Right. So what option will that work out to? So you have P is 3 and Q is 1 and R is 2. Yeah. So option P. So this is the answer to this one. Right. Any doubts in this? No. Let's go to the next question. Identify the water distribution system layout. So let's go option by option from the last one. Is it a radial system? Is it a radial system? Okay, let's come back. Is it a dead end system?
No, ma'am. It's not a dead end.
It's
No.
not a dead end system. That everybody's sure it's not a dead end system. Is it an interlaced system? Okay, let's come back. Is it a ring system?
I think it's ring system.
Okay, somebody says that it is a ring system. Fine. So let's see one by one. So by radial system, what we mean is that there is direction of or supply direction is along, it's radially outside. For instance, if I have a grid, something like this, and if I have the pumping from here, so I'm pumping to this direction, I'm pumping to this direction. So radially, I'm pumping to all the directions. This can also have a diagonal direction also. Let this diagonal go through this. So then I'm diagonally also pumping out. So all this constitute a radial system. So for instance, whenever there are intersections in the piping, there would be a pumping or a water distribution originating from there, and radially we would distribute it outside. So that's what is a radial system. For instance, you will have it radially out to all this direction. That's a radial system. So here there is no radially moving out, nothing is moving radially moving outside. So this is not a radial system. Now dead end system, I guess all of you agreed that this is not a dead end system. So that's already understood. You have something and then it just keeps branching out, and finally there is a dead end. So the advantage of this system is that you can keep increasing this because it's a dead end. You can put another connection and you can increase it from here, provided you have those facilities. But also, in case there is something you cannot increase it any further, like for instance there's some obstruction, then that becomes a bit difficult. What is the other advantage of this? Sorry, what is one major disadvantage of dead end system? So the main disadvantage of dead end system is that if there is, like for instance, it's originating from here, it's going like this, it's going this way. So if there is some leakage in the pipe, or if there's some failure in the system at some point, then everywhere it's affected. For instance, if this pipe is not there, then it doesn't have a parallel method of getting water. So the entire system would be broken, and that place would not receive any water for the duration until we fix this pipe. So that's one major disadvantage because it's all branching out. If one branch is broken, then the entire region is suffered because of that. Whereas all the other systems, laced, radial, even in the radial system, for instance, if I have a house over here, I would be getting water from this pumping distribution, from this side also, from this side also, from this side also. So which means there are multiple paths by which I can get the water. So this problem of system breakdown may not happen, or it's a bit less in the other systems. So that was dead end system. Now you have the interlaced system. So in interlaced system, you have certain primary grid lines going. So this is a primary grid line. It can be horizontal and it can be vertical. And from these primary grid lines, certain small tertiary small grid lines also originate. So it's a grid ion, or you have a proper grid, and from these grids there are small other grids which originates and it's pumped. So the advantage of this again is that you get water from two directions. So even if there's a breakdown, then it can be taken care of. So that is an interlay system. So interlay system is known by several names. It's called as a grid ion system, interlay system. So all this forms in the same one. So basically you will have one main line. So this is your, if this is your main line, then all this becomes your secondary lines. Or if this is your main lines, then all others become your secondary line. So that is about interlay system. So is this an interlay system that we have over here? No, this is still not an interlay system because this is a ring system. Why? Because in ring system, you have the outer perimeter or the outer rings of the entire system will be the main distribution channels, and then inside you will have the minor distribution channels. For instance, if in this example which is given, you have the outer ring through which the main distribution is running. So this is the main distribution and it's going through the outer ring, and inside you have these minor distribution systems, distribution pipelines which are going, and yeah, and then they are interlacing at certain points. So this is a ring system. Now ring system, this is a rectangle one. It can be a radial also, like for instance you have something like this, and then water is going this way, and then you can have minor grids from each of the this main grid which is going. So this is also possible, or in any other shape it can be. So the whole point is that you have your main, yeah, so the whole point is that you have your main distribution system lying in the outer perimeter. That's it. Right. So this is a ring system. So option A is the correct answer. Any doubts in this? Shall we proceed on? Okay, great. Let's proceed on. So question 3. Which statement among the given statement is incorrect? A. Helium is used to detect water leakage in the distribution system. B. Water pipes laid in parallel induce the same head loss in each pipe. C. Velocity of water in the pipe is inversely proportional to the hydraulic radius of the pipe. D. Hazen-Williams formula incorporates the frictional properties of pipe material. So all these options are from different chapters, different discussion regions. So let's go option by option. First one, A. Helium is used to detect water leakage in the distribution system. Is this correct? Okay. Any guesses? How many of you feel it's correct?
Yes, correct.
Correct. Yes. Okay. Somebody feels it's correct. Others feel okay. So yeah. So this is actually a correct answer because we have learned about two methods of understanding water leakage. Or before finalizing the pipe design, we saw that we do an air test or a water test. So in air test, we pass air through the pipe in order to see whether air is flowing properly, whether there's any leakage and all that. We look through the air test. So helium, being a very inert gas, it's mainly used in order to test this. And these are in even in a laboratory setting also, this is usually used in order to in order to find out leakages in any system, any joineries which are there, not just for water distribution system, but a general principle in order to find out how air is moving. If you want to see the spread of air in certain air conditioning systems, or if you want to see whether the systems are interlocked properly, if the connections are proper, for that also we use helium. And these are normally known as tracer gas experiments. So he experiments. So by tracer gas, we are talking about any gas which can trace the path of the gas can be traced. So for most of the tracer gas experiments, it's helium which is used. So in our water distribution systems also, we use helium in order to see whether there's some leakage. Why? Mainly because you can actually, if you're using infrared camera, you can actually see the helium movement of the helium gases through it. Whereas if it's normal air which you're using, visibly we may not be able to see air movement. So because of that, we use helium, or these experiments are usually conducted. So A is the correct answer. Now B. water pipes laid in parallel induce the same head loss in each pipe. Is it correct?
Yes.
Yes.
Yes, ma'am.
Yes, it's correct. So what changes? So this is we are talking about parallel. So in parallel, if it is the same head loss, what changes? Okay, so we have something. So I'm saying this is a parallel connection. These are joints which I'm showing. So we are saying that the head loss remains the same. Now this is a series connection. Okay, so in series connection, does the head loss remain the same? No. So in series, each of these connections, if we have different connections, each will have different heads. We'll have to calculate. Why? Because now if the based on the property or whenever there's a join which is there, the head loss changes. But the discharge through each, like for instance, if there's Q volume of water flowing through this, that volume is not changing, it will be the same. So the discharge or the volume of water which is flowing through the pipe changes, but the head loss changes in each pipe. This we'll have to separately calculate. We saw when we're calculating head loss, it has got three components. So we have the head loss due to suction, due to discharge, and then due to friction also, or friction by which we mainly talk about the distance through which it has to be taken. So in this, the distance changes, right? So at this point, if it's just five kilometers, now at this point this is getting 10 kilometers. So in a series connection, when we look, this is one aspect, the distance changes. Also some frictional properties may also change if it is different kind of pipe, provided it's the same kind of pipe. Whenever we're moving in series connection, the head loss in each section changes, but the discharge remains the same. Whereas in parallel, it is the discharge which changes, because if it's Q discharge coming over here, it becomes Q1 and Q2. It might be the same, Q1 will be equal to Q2, but it is not equal to Q. That is the whole point. The discharge gets reduced. So whatever discharge which was there, that discharge is getting split right now. And but the head loss in each of this remains the same. In the head loss in Q, this pipe, or let's say A and B, will be the same. So that's what is asked over here. In water pipes laid in parallel, will induce the same head loss in each pipe, which is correct because the distance where it's traveling from that point is the same. So the head loss mainly remains the same, but your discharge is one that changes. So this is the correct answer. So here we've been asked to mark the incorrect answer. So all these is not the answer for this question. Now the next one, velocity. Velocity of water in the pipe is inversely proportional to the hydraulic radius of the pipe. Is it correct?
Incorrect. Incorrect.
Incorrect. Velocity. So velocity is directly proportional to the hydraulic radius, is what is said.
Yes.
Why do you say so?
It's Manning formula 1 by n r raised to 0.53 n s is 2. So it is directly proportional.
Correct. We're using, yeah, exactly. So we have Manning's formula. So just to explain that for everybody, Manning's formula says V is equal to 1 by n, R raised to 2 by 3, S raised to 1 by 2. So we have V is directly proportional to R raised to 2 by 3. So it is a directly proportional sign. And here it says that velocity is inversely proportional. So which means this is not correct, which means it has the possibility to be the correct answer for this one. Right. Now, option D. Hazen-Williams formula incorporates the frictional properties of pipe material. Is that correct?
Correct.
It's correct. Yes, it incorporates the frictional properties of pipe material. Okay, so let me just write Hazen-Williams formula. V is equal to 0.85 into CH into R raised to 0.63 into S raised to 0.54. This is the formula where our CH is the coefficient of hydraulic capacity and R is our hydraulic radius. And what is S? What is S in Hazen-Williams formula?
Gradient.
Sorry?
Hydraulic gradient.
Yeah, it is a slope of the hydraulic gradient.
Nope.
Yeah, it is a slope of the hydraulic gradient. Right. So now incorporates the frictional properties of pipe material, but in which of this is the frictional properties of pipe material coming into play? You have hydraulic capacity, hydraulic rate. In hydraulic capacity, do you have frictional properties of pipe material? You have hydraulic radius, and then you also have hydraulic slope of hydraulic gradient. The answer is right. Hazen-Williams formula incorporates the frictional properties of pipe material, but where is it coming in the formula?
CH. CH is the CH indicates the
CH
property of pipe.
indicates property of pipe, okay. Um, but does it incorporate the frictional properties also? Pipe
Not full.
material to an extent I take frictional properties. Yeah, it takes to an extent, okay, maybe, but then the main one which comes is in this one 0.85. So this one is actually calculated. So this hydraulic capacity, yes, to an extent you can say yes, it is different for different pipes. We are solving it in that way also, but by default we do not actually do any calculation, or we do not say that for this particular case we are taking this one. So maybe a combination of this, but actually it comes in this 0.85, where it says that this we have got this factor 0.85 by calculating a hydraulic radius of 1 feet, and we are taking a frictional slope of 1 is to 1000. So for this frictional slope, we have got 0.85. So that is why we say that Hazen-Williams formula is mainly applicable for this particular case where you have this frictional property, frictional slope of 1 is to 1000. And yes, to an extent in your hydraulic capacity also we are adjusting it. But the reason why Hazen-Williams formula is not suitable for all cases is because we are taking this frictional property into consideration in this factor 0.85. That is why Hazen-Williams formula can sometimes give you very incorrect answers also. So we cannot use this formula everywhere. Even though we usually use it for a general purpose, we need to be very cautious while using it because this property is inbuilt in Hazen-Williams formula, the frictional property. Right. Any doubts in this? No. So the answer for this is also wrong. So the answer is C. Velocity of water in the pipe is inversely proportional to the hydraulic radius of the pipe. That's the correct answer. Okay, let's proceed on to the next question. Yeah, so was to explain this one. Yeah. So 4 and 5 is a numerical. So let's try to solve this together. For a city with population 10 lakh and a water consumption rate of 200 liters per capita per day, water needs to be supplied. Flow velocity of water in pipes is 1.6 meter per second. Coefficient of hydraulic capacity is 130, full stop. Maximum daily demand is 1.8 times the average daily demand. So the first question, that is question 4, is asking us to find the diameter of the supply pipes leading to an adequate service in the reservoir. So in meters. So let's see what all information do we have. So we have population 10 lakhs. So population is given to be okay, 10 lakhs itself, and the water consumption rate is 200 LPCD. So consumption rate is given to be 200 LPCD, and water flow velocity in the pipes is given to be 1.6 meter per second. So velocity is given 1.6 meter per second. Coefficient of hydraulic capacity is 130. So coefficient, which is our CH, which is 130. And we've all, so this is something which we already know, that if we have a average demand, to convert it into maximum demand, we will multiply it with 1.8 times. So that's there. So let's just write it. Maximum demand is 1.8 times the average demand. But what is the average demand? We can get it from this, but we'll have to calculate what will be the average demand. So we will do that. And we have been asked to find the diameter. So let's start. In order to find the diameter, the only thing that we have velocity, we know the velocity, and we also know the rate of pumping, which means volume also to an extent we will be able to get, and we've been asked to find the diameter. So we can use a simple formula that velocity is equal to discharge by area. In this, we know velocity, we know like we can find discharge also. If that is the case, we will be an area, we know that it's pi, if it's d, pi d square by 4. So then from that we will be able to find d. So we'll go by this approach. So our first task will be to find q. What is q? Because we do not know what q is. So let's take, in this case, let's find out what is the, so since it's given the maximum daily demand is 1.8 times the average demand, we need to take the max, we need to find that first. So q max will now be 1.8 times the average demand, which is into 200, which will be in LPCD. How much will it be? Now it won't be LPCD anymore, per capita, because it is per day. For one day, what will be the maximum demand? Yes, 1.8 into 200. 1.8 into 200.
3600.
360. Yeah, so three, correct. So one thing is that the average demand is given in LPCD, correct? Yeah. So this is it will be just 360 LPCD, no, 1.8 into 200. So it's 360 LPCD. Now we have to find the daily demand. Yeah. So you need to serve the whole population, right? So in order to serve all these populations, so this is per capita. So for the given population, the total flow would be now this 360 into our 10 raised to 6, because the population is 10 raised to 6, it is 10 lakh is the population. So this is liters per day is what we are getting in this. For the app, in a day, the maximum daily demand in one day will be 360 into 10 raised to 6. Now this one is in LPCD, but in order to use a formula and we need to find it in meters, so let's convert it into meter cube per second. We need to convert it into meter cube per second. So can we quickly convert, yeah, can we quickly convert 360 into 10 raised to 6 LPCD into meter cube per second? How much does it come out to? So the conversion is simple, right? So this is per day. So in convert it into seconds into 24 into
4.160.
4.1666. Yes, correct. 4.166. It would just keep going like that, meter cube per second. Very good. So now we have got Q also. Now let's put it back in our formula. V is equal to Q by A. So V, what is V? Let's just go back to the question. We already wrote velocity is 1.6 meter per second. 1.6 meter per second. So 1.6 is equal to Q in this case right now would be 4 into 1.666, right? Divided by area. So pi by 4 d square. Now we can easily find D. So let's find D.
I'm 2.3 meters.
Okay, what did d square work out to for you?
I'm sorry, ma'am. I left 1.6 behind.
Huh.
3.31.
Okay, d square is 3.31. Very good. So what does 3.32, 1 point something it goes, so 3.32. So what does d work out to?
1.82 meters.
1.82.
Correct, 1.82 meters. So is it there in any of our options? Yeah, option B, 1.82. So this is the answer. Right, so this is very simple in order to find this. We are just using a very simple formula. Velocity is equal to discharge by area. Okay. So let's go to the next part of this. Next part, which is question 5. So this is the same thing. Next part is determine the hydraulic gradients of the pipe using Hazen-Williams formula. So again, to write what was Hazen-Williams formula? V is equal to 0.85 into CH into R raised to 0.63 into S raised to 0.54. Right. So in this, our CH is already given, which is the coefficient of hydraulic capacity. Where is it given in the question? CH is equal to, yeah, coefficient of hydraulic capacity is 130. So CH is given to be 130. Now R, we already found D. So from D, we can find what R is. Uh, but okay, so this D, what we got is the diameter of the pipe, right? Like, so this is the diameter of the supply pipe. Now, this R, what we are talking about, if we just divide the diameter by 2, will we get R? Is it the same radius and diameter that we're talking about?
No.
No, no. Here we are talking about hydraulic radius. Could you kindly explain what is the difference between hydraulic radius and normal radius?
Actually, R is equal to A by P.
A by P. Okay. This hydraulic radius is equal to A by P. A by P, which means area by perimeter.
Yes.
Is there something more to add on to it?
Mm, it is approximately, I think, R by 4.
Ah, that's the point. R by
D by
4, R by 4.
sorry, D by 4.
Okay, yeah, D by 4, correct. Yeah, D by 4. But should it be D by 4 in all the cases? It need not be. That is why. So because I guess that this is one place where you need to clear the confusion. Hydraulic radius is not just area by perimeter. It is area by wetted perimeter. By wetted perimeter, what we mean is that if the pipe is only flowing half full, or if it is only quarter full, which means the area that gets wet in a pipe. So if the pipe is only half full, that means your perimeter is only half of the pipe. It's not the entire pipe. So that's why we take the hydraulic radius in order to consider whether the pipe is flowing fully full or half full. So we always take that assumption. So in this particular question is something given where the pipe is populated supply flow velocity. Okay, it's not given. So which means if it's not given, we always assume that the pipe is flowing full. But in the next questions, I think here or yeah, we will do another question where we are given that the pipe is only half full. So in that case, the wetted bed, this would again change. It would then be d by 2 because only half of the perimeter, we will be considering only half of the perimeter. I mean, we will see that. Need not worry about it. But the whole point is that hydraulic radius is area by wetted perimeter. It's not just area by perimeter. So in this particular case, we know D, what D is. So if R is for a circular pipe, in this case we can say area by perimeter, and we can say it will be this one. If it's in terms of D, then we'll have pi by 4 D square divided by pi D. So we can say that it is pi will get cancelled out. It is D by 4. Correctly as what was pointed out, it D by 4 if the pipe is flowing full. So that is the assumption that we are taking. So in this case, it is D by 4. Correct. Now, what is S? S is the slope of hydraulic gradient. Is that given in the question somewhere? No, slope of hydraulic gradient is this. Okay, sorry, that is what we have to find. Determine the hydraulic gradient. So, which means S is what we have to find. So, this is what we have to find. V. Now, V is also given, right? The velocity of flow is given 1.6. So, we know V, we know all this. So, I think S is the only thing which is unknown. So, we can easily find it. So, let's substitute 1.6 is equal to 0.85 into 130 into, now in this case it's d by 4, so the d was 1.82 divided by 4, the whole raised to 0.63 into s raised to 0.54. So let's solve this for s.
Um,
Yes.
how is it 0.3? Is it
Point
0.13?
0.13 is what? Is it s raised to 0.54 or s?
Yes, 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 ma'am.
S is what is s raised to 0.54?
0.023.
0.023. Uh, just check once more. Is it 0.023 or is it 0. Okay, 0.023. Correct, correct. Yeah, S is 0.023. Good. So then what is S? What did you say S was?
0.13.
How? If S raised to 0.54 is 0.023, then S would be
Actually,
point,
it will be 0.00065.
0.00065. Okay. This is what you're doing, right? The root of S raised to
I
0.054
have,
is
no, I have gone somewhere wrong. 0.019. I am getting 0.019 raised to 1 upon 0.54. I may be
0.01. Okay, so you're getting this value to be 0.019.
yes, yes.
This is the 0.023 is correct over here. 1.6 divided by
Um,
0.85
it's
into
9.7 into 10 to the power minus 4.
correct. 10 to the power minus 4. One sec. 9, 1, 2, 3, 4. Correct. Yeah, that is a correct answer. 9.7 into 10 to the power minus 4 is correct answer. Or if you take it in terms of percentage, it would, or if I just write it, 0.00098. This is what you will be getting. Now, if you look at the options, everything is given in terms of percentage. So if you take it in terms of percentage, two that decimal places will also go. So it will be these two will go, yeah, 0.098 percentage. This is what you should get eventually. So S raised to 0.054 should be 0.023, and when we take the root of when we do the inverse by taking the root, it should give you this answer, and then we convert it into percentage. So this is the final answer, which is there in our option B, 0.0098. Any doubts in this question? No doubts? Okay, let's proceed further. The complex looped network of water distribution can be analyzed by using which of the following? A. Equivalent pipe method. Newton-Raphson method, linear theory approach, Hardy-Cross method. So let's go option by option. Did I miss any question? Yeah, okay. So let's go option by option. Yeah. So the complex loop network, equivalent pipe method. Can we use it? Complex loop method. What was equivalent pipe method? So we have a pipe like this, and if it's branching out into two different pipes, and if it's coming at some point, it's again coming back, or it's just branching out and then going. What equivalent pipe method does is, whenever there's a branch, it considers this to be an equivalent pipe, or the flow, like you merge the whole flow which is there in this pipe into an equivalent pipe, and then you find the equivalent diameter of the pipe in order to do the calculation to see how much of flow should be given to each pipe. So that's equivalent pipe method, and that's mainly used for simple network. So this is a network, right? This is a pipe network, like it's going, and let's say it's coming back. So this is a network. So this is a simple network. So equivalent pipe method, we mainly use it for simple looped networks, but for complex loop networks, we need to go for Newton-Raphson method, linear theory method, or Hardy-Cross method. So by complex loop, we mean if that this is a simple one, it's going. Now here there are two small loops. So there is one loop here, there is one loop here. Now imagine again there is one more loop here. Now this is three other loops. So there are so many. There's a loop within a loop. So this itself becomes a loop. Now within it, three small loops. Now then there is another loop. So there are loop within loops. So that is a complex loop network. So to solve complex loop network, an equivalent pipe method cannot be used. We need to go with Newton-Raphson, linear theory, or Hardy-Cross. We did not discuss in detail on how these methods, how do we use them. We discussed how this has to be done, but each we did not go into very much detail because we have to make certain assumptions. So to give a simple, to explain at a very high level, we assume the flow Q through this one, and then if this is Q, we assume what is Q1, what is Q2, we solve. And finally, based on the value that you're getting, because it's a loop, we change the assumption of Q. So then Q becomes Q dash. And then we again solve in order to get what should be Q1 dash, Q2 dash. So we start with an assumption and then we finally come on to the final value. So we need not go into the details of that, but the idea is that all three of these methods are what is used. So answer is B, C, and D, which is there over here. I think, yeah, so this is what we learned in our lecture also. So method for analyzing complex pipe is that we use Hardy-Cross, linear theory, and Newton-Raphson. And how we do is that we network balancing by solving a set of linear simultaneous equations in the pi flow. So in order to solve these equations, we need some assumptions. So that's why we start with some assumptions and simultaneously we solve all these non-linear equations, and then we finally come to find out, finally we improve our assumption based on this and we come to a value for our assumption. Right. So any doubts in this question? Shall we proceed further? Okay. So we'll proceed further. In question 8, the question is, Chessy's formula for open channel flow does not consider which of the following? Firstly, what is Chessy's formula? Can anybody recollect? Sorry, I went to a different question. Yeah. I know we learned a lot of formulas, so I'm just giving you. It's Q is equal to A into C root Mi, where Q is a discharge, that was what we are trying to find, and area is the A is our area of flow, and C,
Coefficient.
yeah, C is a coefficient. It's the Chessy's coefficient, and Mi is the slope of the bed. Sorry, not Mi. I is the slope of the bed, and M is the hydraulic. Correct. Hydraulic. What is it? Hydraulic?
Mean depth.
Yeah. So it's the hydraulic mean. It is also the hydraulic radius. Hydraulic radius or hydraulic mean, it's sometimes used differently. So previous one, we spoke about hydraulic radius. So that's also, it's also the same here because we're using M, we call it the hydraulic mean. So now let's see. Chessy's formula. What does it not consider? Hydraulic mean depth. Does it consider the hydraulic mean depth? Yes, it considers. So it's mainly from the hydraulic radius that we're talking about the mean depth or hydraulic mean. So it considers hydraulic mean. Uh, Now, slope of the pipe, does it consider slope of the pipe? Yes, because that's what is over here, slope of flow. So the slope of pipe is also important. Length of the pipe, does it consider the length of the pipe?
No.
No, because we don't have it anywhere in the formula. We just have area, coefficient, slope, and the hydraulic mean. So it does not consider area of flow. Yes. So the answer to this is length of pipe. Okay. Any doubts? Shall we proceed? Okay, we are proceeding on to the next question. Dash are used to determine the volumetric flow of water directly from its velocity. So we are mainly talking about certain meters which are used because all of these are different meters. So which meter is used in order to find the volumetric flow directly from its velocity? So let's go from the last one. Inferential meters. Is it inferential meters? Okay, ultrasonic meters, electromagnetic meters, rotary piston meters. Any guesses which one? Okay, so I'll give you a hint. They have asked about volumetric flow directly from its velocity. So which of this calculates a volumetric flow by using volume? Just say which calculates. So electromagnetic meter does not directly take the velocity and volume. So we can give this. Ultrasonic meter also, it's based on certain distance. Ultrasonic waves, it has to travel certain distance. So it's mainly based on reflection of the, we cal we calculate the flow based on certain reflective properties, and it doesn't calculate the volumetric flow from velocity, so it's not that. Then so let's go into the theory and then we will see. So we have volumetric meters. So this is the volumetric meter, and rotary piston is an example of volumetric meter. So this is the answer for this one, rotary piston, because they've asked to find what is a volumetric flow which is calculated directly from the velocity, and rotary piston is a volumetric meter which by property it calculates from its velocity. But let's see the other ones also. What is electromagnetic meter does? So it has a magnetic, so it creates a magnetic field across the pipe. And whenever there is movement of water, because there's a magnetic field, so we have learned, like if you have a magnetic field around and when there is movement, it induces certain electricity. So we have learned in our school, by movement, when a magnetic field, when something is moved across a magnetic field, then it can induce some electricity inside it. So because of this, uh, yeah, so the magnetic field is created across the pipe, and because of this, there's a voltage. It induces a voltage difference, and this voltage difference is directly proportional to the flow velocity. So you measure the voltage. So the question was volumetric flow. So this doesn't take the volumetric flow, it takes the voltage and then it calculates what is the flow velocity. So that is what electromagnetic meters does. Now, what does inferential meter do? So it can inferential meters can also infer the volumetric flow from the velocity. Oh, so yeah, so I think both will be, inferential was given. Yeah, so both are correct. So you have inferential meters and rotary piston meters. Both will be there because this also directly takes it from the velocity, volumetric flow directly from the velocity. So jet meters are used. And then you have ultrasonic meters. So this is what I was explaining before. So it mainly looks at the time. So you have sound waves. So there are certain sound waves, and when the water is, so sound waves slow down when that water is flowing through the pipe. So based on this time in which we get the reflection of sound waves, based on this, whenever they're flowing with the flow, based on this, so based on the speed of the reflection, that mainly we're talking about the time. So based on this, we calculate what is the velocity of flow. If it's moving fast, then the reflection or the time is different based on that. So that is what. So that's what is given over here. The sound waves slow down when moving through the water against the flow and speed up when they're moving with the flow. So based on this, you get the direction where it's moving. It's moving towards us or whether it's moving away from us. So that is what is ultrasonic. So the answer for this is that in order to determine the flow, so directly I think inferential meters is more appropriate because it's directly from the velocity, but rotary piston meters also takes the volumetric flow by looking measure the volumetric flow directly. So if the question is asked this way, you can mark both the answers. But if there's only one option correct, then inferential meters is the correct answer. Okay, let's go to the next question. The pipe materials, was there any doubt in the previous question? Sorry. No. So let's proceed. The pipe materials that are commonly used now in water distribution lines are glass reinforced pipe, polyvinyl chloride, high density polythene, asbestos. So more than one option can be correct.
PVC and HDPE.
PVC and HDPE, yes,
Seam.
they are used. What about glass reinforced plastic? Is it not used?
Not most commonly used.
Uh, okay, yeah, actually, that's a debatable one because they have said most commonly used. So yeah, but glass reinforced plastic is also used these days. But asbestos cement, is that used?
Earlier it was used,
Exactly.
not
Earlier it was used. Now it's not used. Why has it been discontinued? Any idea?
Scouring.
Scouring, maybe, but mainly the reason is that it has certain health like side effects also. For instance, asbestos fibers recently it's been identified to have major risk issues for workers or anyone who comes in contact with it. So mainly it has been reported that it causes lung cancer and all when inhaled. So because of that, because of certain uh, because this material is causing adding on to the impurities of the water, because of that it's not used. So it was earlier which was used, and by how it's affecting is because this has components which are, yeah, so these fibers emit has these components which can cause these lung diseases and all that. So because of that, even though earlier it was used, right now it's not used. So yeah, so this is something new. Let's go to the next question. Last one, sorry, question 11. Dash has a least coefficient of thermal expansion. UPVC pipe, concrete pipes, cast iron pipes, and high density polyurethane pipes. Which one? So we are talking about, sorry, I think I just showed the answer. Yeah, we are talking about thermal expansion. Least thermal expansion. So again, it's concrete pipes because all the other pipes, it's a material property. So all the other pipes, it's there. But among all this concrete pipes, so concrete, uh, by nature of it, it has least coefficient of thermal expansion, which means when due to heat, it doesn't expand or it doesn't deform much. Whereas UPVC pipes, when it's subjected to heat, it has a tendency to expand more. So the coefficient of thermal expansion for these pipes are much lesser much higher compared to concrete pipes. So the answer for this one is concrete pipes. So we have this over here. So yeah, so coefficient of thermal expansion describes how the size of the object changes with change in temperature. So it that's what I was explaining before, that it the deformation which is there. And for concrete pipes, the deformation or thermal expansion is least, so it does not deform much. So this is a material property. There's nothing to think much in this. So we'll proceed to the next question. Yeah, so this is an interesting question. We have learned about different joints, so we have to mark the joints. So first one, screw joint. So which of the following correctly depicts screw joint?
last one.
Third one.
All of you are saying third one. Okay. So let's see. Third one. Anybody, any difference of opinion?
Second.
Okay. Somebody says second also. Fine. Anybody says first? No. Okay. Let's see. Which is flanked joint then?
Third one.
Okay, Vaishaka gave this has okay, so this is Vaishaka's options. So others who said screwed as a third one, which is flanked. It's one or two. It has to be one or two, right? Any guesses? No. Okay, what is last one? Spigot and socket joint.
First.
First one.
Okay, so that there is no confusion. I think everybody has agreed that this is spigot. Okay, so by spigot and socket joint, it means there is a spigot and there's a socket and there's a spigot and you insert the spigot into the socket. So that is correct. So you have a socket and you're inserting the spigot onto this socket. So two pipes are interlinked. So you have one pipe which is a bit bigger and then you have another pipe which is not so big. I mean, the thickness, we're mainly talking about the thickness. So this pipe will be something like this. Eventually, it will have the same thickness, but then where the joint is, it would be a bit opened up so that you can fix it inside. The spigot goes into the socket. So this is right. This relationship is right. Now, it's like let's look at screw joint. So I understand the confusion why a lot of you said that this is screw joint because you might be assuming that there is a screw over here. But this is actually a flanked joint. By flanked joint, what we mean is you have a flanked section. So this is a flanked section. So you've got two flanked sections for the pipe. I mean, this is the pipe, this is the section outside the pipe. So these both are joined, like it's a butt joint which is joined, and after that it is screwed together. So we understand, yes, there is some screw which is being involved in it, but this is a flanked joint. By name, this is a flanked joint because there are two flanked sections being put together in order to join, and then you have like so. This is where this is the joining portion that you have. It's put together. Right. But this is the screw joint because you have two pipes and then you're screwing these pipes together and then you're covering it up. Like so this is the portion where you're finally covering the screws up. So this is the actual screw which goes in which keeps these pipes together over here. And this doesn't have any other section. Like this is the only joint. So you have so this what you see is essentially where the screws are going and then you're covering it up. So this is the screw joint. So Vaishaka was right. P is screw joint is 2, flank joint is 3, and spigot and socket joint is 1. Any doubts in this question? No doubts. Okay. So let's proceed on to the next question. So yeah, so this is a numerical again. Uh, yeah, so this should be very easy because we did a very similar problem in last class in lecture week 4. We discussion on week 4, we already did a similar problem. So let's deep. For a city of population 15 lakhs, 15 lakhs, yeah. The average 15 lakhs, the average water demand is 220 LPCD. Assume the daily maximum demand to be 1.8 times the average demand. Find the size of the supply main pipe used to transport water located at a distance of 20 kilometers. So we are saying that the pipe length. So this statement essentially means that the length of the pipe L has to be 20 kilometers. The loss in head due to friction is 30, which is already given, which means our HF is given to be 30 meters. Now assume F. What was F? We learned about the coefficient, right, last time? So F is given to be point. So we learned Darcy's coefficient. Sorry, this is F dash which is given. Yeah. So directly Darcy's coefficient is given. F dash is given to be 0.012. So this is Darcy's coefficient. So what are we interested to find? We are interested to find the size of the supply main pipe. So size of the supply main pipe. Size of supply main pipe means we are essentially finding the diameter, right? Size, it can be diameter or radius. So we mainly find the diameter. So which formula will we use for this? So we'll use a Darcy-Weightman formula, which we discussed. We discussed previous class also a similar formula in order to find given the like we used it mainly in order to find the loss in pressure or the lift which was required due to friction. That's already given. So we'll see how we can use it. So let's just first see what, so we have population 15 lakhs, 10 raised to 5. Then we have a water demand, which is Q, average demand 220 LPCD, which is given. So let's take Q max also now itself, which is 1.8 into 220. How much does that work out to? We just did it before, so so it's 396 LPCD. The other one was just 200. Here it is 220, so 396 LPCD. Now, if this is the case, the maximum demand for the entire population would be 396 into 15 into 10 raised to 5 LPs, liters, not per capita, for everybody, liters per day. So this will be liters per day. So now, like usual, we need to convert it to meter cube per second. How much does that come out to?
594 into 10 power 6.
594 into 10 to power 6. Okay, you're right. Is somebody else getting a different answer? Okay, everybody is getting 594, then it's good, fine. Then that means there was a, you could have gone wrong somewhere. So that's why I asked if somebody is getting a different answer. If you're all getting the same answer, then it's correct. So this is 5, so this is correct, 594 LPCD. Now convert it into meter cube per second. When you convert it into meter cube per second, one thing which I forgot over here, I think in the question it's a bit, yeah, so one thing is missed in the question, which is there in the assignment question, but I missed it over here, is that the pumping is only for 16 hours. It's not a 24-hour pumping. You're only pumping for 16 hours. That's one important factor which we need to consider, which I missed in the question. Like in the question, there's a statement which says that the pumping is mainly for 16 hours. If that is the case, now let's convert this liters per capita per day, or this is liters per day into meter cube per second. So the catch here is that if you have 594 into 10 raised to 6 LPCD, when you're converting it into meter cube per second, you don't use 24 hours, but you use 16 hours because the pumping is only there for 16 hours. So that is a very important thing in the question, which I'm sorry I missed to type it in the question. So how much in meter cube per second?
Ma'am, is it 10 power 3, ma'am, or 10 power 6?
What I've written, 10 power 6.
594 and 10 power
10 power 6, because it's this, its population is 15 lakhs, right? So when you're adding, when you're multiplying this up, 396 into 15 will give you 5940. So 594 into 10 raised to 6.
10.31.
10.31 meter cube per second, correct. 10.31 meter cube per second. Very good. So now we have got the total maximum demand. Now let's continue. So this is the maximum demand. Now what is the distance where that we have to travel, or the distance, which means the length of the pipe is 20 kilometers, and HL is already given. The loss is already given to be 30 meters. So now, yeah, so we have F dash also, which is 0.012. This is the information which is already given to us. So we know this formula, HL is equal to F dash into L into V square divided by 2GD. Remember seeing this formula somewhere? Last class we solved problems using this formula. So here, last class, but it was not, it was the Famin's coefficient which was given, which was F. Here directly we have Darcy's coefficient is given, so we need not do any conversion. So this is given. So we have this. We have L also, which is our 20 kilometers. What is V? Do we know V? We do not know. That is why we did this Q and Q max. So from that Q max, so we learned while taking this V, we always go with the maximum value. We don't take the average value in order to, like, V is equal to Q by A. That's the formula that we're using. In order to find this Q, we will always go with Q max. So we also know the formula in terms of Q by A, what we will write this as V dash L Q square divided by 2G pi by 4 the whole square into D, sorry, into D raised to 5. This formula also we have written, right? So we will try solving with this formula. Oh, I didn't leave space. Yeah, so we can try solving. Let me just take one more sheet in order to solve that. Yeah, so we can solve. So what is F dash is given to be sorry, HL is given to be 30, which is there in the question, which is equal to our F dash, which is 0.012 into, now our L is 20 kilometers. So I'm writing everything in terms of meters. So 2 into 10 raised to 4. Now our this one Q square. We need to get Q square. So Q is 10.31, right? Yeah, 10.31. We just found that out. So that the whole square divided by pi. So 2 into 9.8, 2G. Pi, let me leave it as pi by 4 the whole square itself. And D raised to 5. So this is what we have to find. D is what you have to find. So let's solve this now.
Two point three four.
What is D raised to 5? How much is D raised to 5 coming?
70.33.
70.33. Okay, good. Yeah, 70.33. So if that is the case, what is D?
2.34.
2.3.
Correct, 2.34. So let's see whether it's there in the option. Yeah, 2.3 is there in the option. So option D, 2.3. That's the answer for this one. So yeah, so the only catch in this question is that you also need to check for how long is there pumping, or for how much duration will the water be flowing through the pipe? Based on that only, you need to convert your liters per capita per day into your meter cube per second, the volume which is flowing. If the pumping was 8 hours, again, which means there would be more concentration of water at that particular hour. So this is a very important factor which you need to consider while doing the calculation. Right. So yes, so let's go to the next question, which is question. Oh, I forgot to put the question number. Yeah, fine. So this is question 14. So let's say choose a system that does not require pumping. Which of the following systems does not require pumping? Lifting. In order to lift, do we need a pump or not?
Yes.
Yes, we need. So this was there in your previous assignment. I know it's a very simple question, but this was there in last year's assignment. So yes, lifting is required. For gravity flow, do we need pumping?
No, ma'am.
No.
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 Yes. For dual flow, we need pumping, right? That's what we discussed
Yes.
the first question. Then for flowing, do we need pumping for flowing?
No, ma'am.
No, okay. So that's a bit tricky to say. We cannot really say that we don't need pumping because it's not specified what kind of flow it is. So yeah, so this question is a bit ambiguous, I understand. But again, when you're asked to choose the best option, you have already got the best option, which means gravity, so you can mark this. If it was marked more than one option, right? Yeah, then it becomes a bit tricky. So for flowing, it's mainly talking about distributing water, or your allowing water, or you're giving a discharge to a certain pipe. So for that, you actually need pumps in certain cases. So we cannot say that you don't need a pump. So yeah, so it's not a very good question. I accept it. But yeah, let's say that it is needed in certain cases. So we cannot say a no to it. But yeah, gravity, if it is a gravity pump system, we definitely do not need pumping. So this is the best answer that we have. Now, the next question, write the full form of AMR. So this was there in our lecture. Is it automatic metering and reading, automatic meter reading, automatic meter reader, automatic meter rendering? Any guesses?
Automatic meter reading.
Automatic meter reading, yeah, that's correct. So it's there in the lecture. It's automatic meter reading itself. So yeah, this again I put it because it was there in the previous assignment. There's nothing to explain in it. It's just the AMR stands for automatic meter reading. Now, next one is, yeah, match the following. So yeah, so this maybe I'll just zoom this a bit. Let's go to the first one. What does this represent? We have radial interlaced tree. Three things, yeah. So the first one, is it
Tree, ma'am.
tree? So we already discussed about dead end system. So dead end system is also called as a tree system. So this one is a tree system, okay. Second one, Q.
Radial.
Radial. We discussed this in the first question itself. So when you have water radiating outside, it's radial. And the last one is interlaced. So this is again we discussed. You have a primary line, and then from the primary line you have multiple grids coming out. So that works out to P3, Q1 and R. So that's B, right? Option B is the answer for this. Fine. Now, next question. Management strategies that cannot be adopted in network design using EPANET. So what is EPANET? Remember from the lectures? It's a software that we use in order to calculate. So water management, which is a management strategy that we cannot use in the network design using EPANET? So first one, change in water height. Can we put change in water height in EPANET? In the last portion, I think last portion, we had discussed this, whatever are the capabilities. So, does any of you remember that? Oh, yes, no? No. Okay. So, yeah, so change in water height, we cannot change the water height in EPANET. Like we have given the water height, we can see the volumetric flow or the discharge frictional factor. So all those factors we can change, but water height we cannot change. Changing source utilization, this we can change the source utilization. If we replace it with a pipe based on the different materials of the pipe, what happens, that we can see. Change in emptying schedules, that also we can see. So mainly this is used in order to uh, see when there are certain changes in sewage design pattern, sewage network pattern, what happens. So all these we can look, but change in water height we cannot, because in the sewage design we are not looking at the change in water height. So this we cannot. So and through APANET we cannot input the change in water height. So that's the answer for this. That cannot be adopted, so we cannot adopt the change in water height. So if you go through the lecture, you will understand that a bit more. So let's go to the next question. Leakage of water in the distribution system can be detected using which of the following? And this is an interesting question. So can flow meters detect the leakage in water uh, distribution system? Yes, no?
Yes.
Yes. Why? Because we will be able to find the volume of flow. So if the volume is reduced, then we know that there is some leakage which is there. Stress meter, can that detect?
Yes.
Stress meter. What is a stress meter measure? Okay. So stress meter gives the water stress, or the pressure which is there inside the pipe. So that if there's a leakage, stress meter can be used in order, yes, so stress meter can also be used in order to find the leakage, because there would be a pressure difference which is there. So stress meter, yes, stress meter can also be used. Now hydraulic gradient line plotting, can that be used?
Yes.
Yes. Why? Because when there is a leakage in the pipe, then the hydraulic gradient line will also change. So just by plotting, so they say that if there's a sudden change in slope of the hydraulic gradient, then that means there is a leakage in pipe. So this is a very common method which is usually used where you don't have any meters installed inside. Just by looking at the hydraulic gradient line, which is there in, by plotting the hydraulic gradient line, we'll be able to find out whether there's a leakage in pipe. So yes, hydraulic gradient meters can also be used. And then the last one is flow analysis equipment. Yes, if flow meters are used, any flow analysis equipment can also be used in order to find, because it again gives, there would be a difference in velocity if there is a leakage. So if you're using a flow analysis equipment, that also. So the answer is option A, B, C, and D. All of these can be used in order to find leakage in a water distribution system. Fine. Let's move to the next. Oh, that's it. 14 questions. Change in. Oh, yeah, that's it. So that's all for. Yeah, so we discussed 18 questions today. So because I forgot to put the number, I thought there's another question. So yeah, so that's it. So do you have any doubts in any of the lectures or any of the content that we have discussed from week 1 to week 5? You can ask now. Nothing. Okay. Uh, Very well. And have you all registered for the exam? I think today is the last day to register for the exam.
Yes, ma'am, registered.
Okay, that's good. Very well. So, if there's nothing else, we can wind up for today. Exam. Yeah, so I think last class also I mentioned somebody had asked about the exam paper pattern. So it will be very similar to the assignments that we are discussing. If somebody was not there in the last class, I'm just repeating it again. It'll be very similar. And somebody had also raised a concern in the discussion forum regarding uh, too many numericals being there. So don't worry, it would be the numericals, very similar numericals what we are solving in class. Nothing new would come. It'll be something which you're already aware of. So don't worry about it. And yeah, so I guess till assignment 4, the answers are also out, right?
Yes.
Yeah, so
Yeah.
you have no doubts in that, right? If you have any doubts in that, those also we can take up during the live sessions. Okay, so very well. So that's it for today then. I will be there till 9 o'clock. If you have any doubts, you can log in and ask. If you have no doubts, then we can call it a day. Thank you all for joining. Thank you.
Thank you, ma'am.
Yeah, good
Thank you.
night.
Thank you.
Thank you, ma'am.